Hi everyone, my name is Jamel Watson Daniels, and I am going to present to you our work on multi-target multiplicity, flexibility and fairness, and target specification under resource constraints. So prediction problems are all around us in decision making throughout society, in health, education, employment, and finance. These real world problems are rarely presented as clearly formulated machine learning prediction tasks. There are often multiple reasonable choices for target variable. This is the focus of our paper, situations where there exist multiple equally good target options. We build on research that connects this flexibility and target specification to algorithmic fairness. Scholars have explored, for example, how different choices in target can lead to more or less disparity in selection rates for individuals in different protected groups. One particularly well known study illustrates the risks and benefits of target specification. This study by Obermeyer examines an algorithm used in healthcare systems to determine patients selected for a high risk care management program. The goal is to target chronically ill patients who need additional care to prevent future health issues. In the paper, they found that the choice to use cost as the target variable led to racial disparities, where Black patients were underrepresented in those selected for the high risk program. This label choice bias has often been interpreted as a lesson in picking the wrong target. We zoom out a bit and consider the more general interpretation that there often exist multiple target options that are reasonable in some sense given the task at hand. So, as a field, we could use a framework for examining target variable options for these types of predictive allocation tasks upfront. That is what we do in this work. We present a generalizable computational framework that focuses on, first, this problem formulation where there are multiple reasonable target options. We do this through the lens of something called model multiplicity from machine learning research, which I'll explain. And we show how this general framing helps to characterize the extent to which target choice affects disparate outcomes. Now, with that high level overview, let's get into our concrete contributions. So, first, we develop methods to evaluate single target multiplicity under resource constraints. Then we introduce the concept of multi target multiplicity alongside some methodology. We use our framework to study fairness related measures, and then we demonstrate on the dataset released with the Obermeyer study. In the single target setting, we first develop methods for predictive multiplicity under resource constraints. So to ground us, let me define the terms. In machine learning, model multiplicity, also known as the Rashomon effect, is defined as the existence of multiple models that perform almost equally well for a prediction task. Predictive multiplicity is the prevalence of conflicting predictions assigned by that set of near optimal models. So for a prediction task, we have some data set with features X, protected attribute A, and target Y, and we would train a model with optimal loss or accuracy. And multiplicity just says that there are multiple models with performance slightly less than the optimal by some epsilon. So this is our single target multiplicity. In terms of predictive multiplicity, one metric reported in the literature is ambiguity. So this is defined as the proportion of individuals assigned conflicting predictions by this set of near optimal models. Conflicting prediction means different things in different settings. So let me show you what that means. In binary classification, a conflicting prediction is when a decision flips between yes and no. Whereas here you can see in B, probabilistic classification, a conflicting risk estimate might change drastically between the optimal model and the near optimal model, but it may not necessarily flip. And now in the present work, for our focus on resource allocation, the rank assigned to individuals can change whether a person is selected to receive a given resource. So in the concept of predictive allocation, a flip or a conflict means that the top ranked individual selected to receive the budget change. So an individual is selected or unselected. That's our flip here. And now our computational approach for evaluating this predictive multiplicity under resource constraints is the following. So we're in the single target setting. So we select a single target and a data set sample. We train some optimal baseline model, and then we analytically compute which points are unflippable, removing those from consideration. And then next, for individuals in the sample, we use mixed integer programming to determine how their rank changes over the set of near optimal models. This allows us to compute which points are flipped, and then we use that to compute ambiguity. With some understanding of the single target multiplicity, now we introduce this concept of multi-target multiplicity. So given multiple target options, we can consider the set of good models that arises from, say, models that predict any individual target well, models that predict a combination of the targets well, or models that combine the predictions of a single target. So in this work, we say if each target option individually has some merit on the basis of predictive allocation, then any combination of those predictions is arguably also a reasonable candidate. So in the paper, we introduced two combining procedures inspired by existing work, and I discussed the index model here. So the index model combines the target options where the weight is a parameter denoted alpha in the paper, and we can determine how much weight to put on each individual target. Here I show cash, or as is illustrated here, or cost, and illness. So we could determine the weights to put on each of those targets, for example, to create an index model. And this gives us our multi-target ambiguity. So we want to know how many individuals are assigned conflicting allocation decisions over combining procedures. So this is how we define our ambiguity. Our computational approach to examining this multi-target ambiguity is as follows. We select multiple reasonable targets, and again, a dataset subsample, and we use integer programming to determine the minimum and maximum rank assigned to each point over the combining procedures. And then again, if the decision between the minimum and maximum flips, then the point is ambiguous, and we use that to compute ambiguity. Now we use our multi-target multiplicity framework to study selection rate disparities, which is related to group fairness concerns. Specifically, we examine how selection rate for members in a protected group change over the index model options. Our computational approach, once again, to studying this is we select multiple reasonable targets and, again, a data set sample, and then we use integer programming to find combining parameters that minimize and maximize the attainable selection rate for a given group. And we can use this to gain insights about our target options when examining the combining parameters that are output by this minimum or maximum formulation. Finally, we demonstrate our framework on a data set released with the Obermeyer study. So we train separate models to predict each of the three target variables: healthcare costs, avoidable costs, active chronic illnesses, and we use the models to rank a held out set of patients. And then we also train the index model for these three target options, and we show our results here in figure 1. So our results show that we are able to fit separate models that are useful for predicting the three outcomes that may be of interest on their own, right? But we also arrive at a way of ranking patients that results in a more equitable allocation of a scarce resource using the index model approach. Here I list, we also have some additional results that I encourage you to check out if you look at our paper. Please see the paper for also our extended related work section and much more discussion. Thank you for your time.